In this video, we're going to talk a little bit about continuity, and we're going to look at a couple of examples of function equations, determining where they're continuous or not, and if there are any discontinuities, classifying those types of discontinuities. So just a little review from previously. Remember that the definition of what it means for a function to be continuous at a point is that the limit as x approaches c of f of x is equal to f of c. So that's a definition you should have memorized and be able to write down. You also want to make sure you're clear about what that means. That means there's really three basic things that have to happen for this to be met. So I'm going to kind of start on this side actually, because this is often where continuity is an issue. F of c has to exist. So that's one thing to check. That's really about domain. There has to be an output for that input at x equals c. So x equals c has to be in the domain of the function is one thing to check. Another thing to check is that the limit as x approaches c of f of x has to exist. So that's another consideration to think about. And then the third thing is that the function output and the limit have to be equal. So they agree with each other. So when we're thinking about where a function might be continuous or might fail to be continuous, I tend to kind of think about it in this sort of hierarchy. First of all, thinking about domain. If a function isn't even defined at a point, then it can't possibly be continuous there. All three of these conditions have to be met in order for this to be true. So if it's not even defined at a point, it kind of doesn't matter whether the limit exists or not, because all three of these have to be met. Once I've kind of established what the domain of the function is, then I might start to think about, are there any other places where we might have some trouble with a limit existing, and consider those limits and then verify that they are equal. So we're going to look at a couple of function equations and determine where they might fail to be continuous, and then so therefore then we can say where they are continuous. The other thing that we're going to do, though, also is classify those discontinuities as removable or non-removable discontinuities. So we'll look at that a little bit. And so we looked at that in a previous video, too, just remembering what that definition is, that a discontinuity is removable if this second condition holds, but one of the other ones, or maybe both of the other ones, failed. So a removable discontinuity has the limit existing but either the function output exists or maybe it exists and they are not equal. Okay, so we're going to look at two function equation examples and determine where the function might fail to be continuous. So we're going to look for some violations of these conditions. And if we find any places where it fails to be discontinuous, then we're going to figure out whether we have a removable or a non-removable discontinuity. All right, so the first equation that we're going to look at is f of x equals x squared over x minus 3. Okay, so when I look at this function and I'm thinking about where this function is continuous, or the other side of that question is where does it fail to be continuous, where does it have discontinuities, I would start looking for reasons where one of these things might fail to happen. So this first question is really about domain. So when I look at this function, one of the first things I should think about is what is the domain of this function. And the domain of this function is all values of x except 3. X equals 3 would make the denominator 0, so that's not in the domain. So I'm going to write the domain in interval notation here. All right, so x equals 3 is not in the domain of the function. Which means, another way of saying that f of 3 does not exist. There is no output when I put in x equals 3. So x equals 3 is not a place where this function is continuous. So I have a discontinuity. at x equals 3. F of c does not exist when x is 3. So we have a discontinuity there. The other thing I might then start to think about is, are there any places where the limit might fail to exist? So any places other than 3 where I might need to think a little bit about the limit and have some trouble with considering the limit. So let's just think about an example here. If I were considering, say, a limit as x approached 1 of a function like this. Okay, so if I was considering a function like this and I was thinking about a limit as x approached 1, we know how to do that. And you can probably write down that the answer to that limit is -1/2 pretty easily. You're using a substitution shortcut theorem for rational functions. And so really, the only value of x for which you could not use a substitution shortcut theorem for rational functions here would be the value of x that would make this denominator 0. And so this substitution shortcut works for everything except x equals 3, which would make the denominator 0. So I used 1 as an example here, but for all values of x besides 3, I could do this to find the limit, which means that the limit does exist. Right? So function output limit exists, and in fact how I found that limit was just plugging into the function. So I was finding f of c, and I used the fact that they're going to be equal. Those substitution shortcut theorems in essence are really about continuity of the function. We hadn't talked about continuity yet when we covered those theorems, but that's in essence what those theorems are really about, is understanding that you can sometimes substitute in, which is finding f of c, when you're trying to find a limit and claiming that they are equal. All right, so the only discontinuity for this function would be at x equals 3. So we could say that this function has a discontinuity at x equals 3, and it's going to be continuous everywhere else. So you want to pay attention to how the question is asked. If it asks where are the discontinuities or where is the function continuous, it's kind of the two sides of the same question. Continuous actually on its domain for this question. So either of these could be answers to a question about continuity depending upon what was asked. The other thing that we might think about is whether this discontinuity is removable or non-removable. So we might think a little bit about the limit as x approaches 3 of this function and think about whether that limit exists or not. So we can't use a substitution shortcut theorem to find the limit as x approaches 3 of that function. I can't substitute in there. There's not a lot of simplifying I can do. I could look at a graph of the function near x equals 3 and think about that. Or we could go back to how we kind of started with these limits and think about making a table of values where I look at some values of x that are slightly larger than 3, some values of x that are slightly smaller than 3, consider those two one-sided limits and see what happens with that. So if you make a table of values, one of the things that you should find is that on one side of x equals 3, those function output values are headed toward one place. And on the other side of x equals 3, those function output values are headed toward another place. So this limit does not exist. You should make a table of values or look at a graph and verify that for yourself. But this limit does not exist, which means that this discontinuity that we have here at x equals 3 is not a removable discontinuity. We would say that that is a non-removable discontinuity. Non-removable discontinuity. All right, let's look at another function. I'm actually going to just modify this function a tiny little bit. And so some of the same things that we talked about will apply. We're going to call this a new function. Let's call this one g of x. And I'm just going to change the numerator a little bit. So we'll have x squared minus 9 over x minus 3. All right, this function has the same domain as the function we just looked at. That's really about the fact that the denominator would be 0 if I tried to plug in x equals 3. So we still have the same domain. X equals 3 is not in the domain of this function either. So this function also has a discontinuity at x equals 3 because that's not in the domain because f or g, we call this one g of 3 is undefined, does not exist. So that function is discontinuous at x equals 3 because g of 3 is undefined. I can't plug in 3. 3 is not in the domain. In order to think about whether that discontinuity is removable or non-removable, I want to think about the limit as x approaches 3. Okay, so this example should be familiar to you. We did some like this a few sections ago when we first started some limit theorems. One of the things that you might think about is simplifying this function. And so if you factor the numerator, you can rewrite this as the limit as x approaches 3 of x plus 3 times x minus 3 all over x minus 3. And then you might cancel these factors. When you do that, remember that you're not getting exactly the same function. You're getting a new function, which has a different domain, but they agree at every point except when x is 3. So we have a theorem about functions that agree at all but one point, which says these two functions have the same limit. And this new simplified version that has different domain is defined everywhere. It's a polynomial function, so we can use a substitution shortcut to get that limit. 3 plus 3 is 6. Okay, so for this second function, we have a discontinuity at x equals 3 because the function's undefined. That's the only place there is a discontinuity for the same reason that we talked about over here. But for this one, that discontinuity, because the limit exists at that point but fails the condition about the function being defined, this discontinuity is a removable discontinuity. So this one is a removable discontinuity at x equals 3, which is a removable discontinuity. In terms of the graph, what that means for the graph of that function is that I would expect there to be a hole in the graph at the point 3, 6. The hole is there in the graph. That's what this tells us. There's no point at x equals 3. But when the function gets close to x equals 3, it's closing in on the same value. That would have a y coordinate getting infinitely close to 6. All right, so we'll look at some more graphs of functions and some more continuity examples. We're going to look at a piecewise function in the next video.